Welcome back to another video. If there's one single most important law in this course, it's the strong law of large numbers. And that's the topic of today. It's a result which you know because it basically tells you if you throw a die very often, the 6 comes approximately in the fraction of 1 over 6 of all times. Put differently, if you have random variables, lots of them, and they are equally distributed, then their mean will become their expectation. So that's the law of large numbers. There's a limit result, and the limit, as we know, can be, for example, almost true convergence or a convergence in probability. In the basic probability course, you heard about the weak law of large numbers, and this is the result using convergence in probability. And today, our task is to prove the strong law of large numbers, which is the same result, but with almost true convergence. Let's get started. So, the strong law of large numbers. Let's recall what I just said from basic probability. There you had the following proof. Take some random variables which are in L2, so real valued and in L2, and some small number epsilon bigger than 0. And the probability, the random variables are IID. Then the average, or the average distance to the expectation. So this is exactly this here. The average distance to the expectation. The probability that this here is bigger than epsilon goes to 0. And since this holds for every epsilon, you might also say that this here converges to 0 in probability, by definition of convergence in probability. The proof of this was actually quite simple. It uses the Chebyshev inequality. So we have some non-negative random variable here, bigger than epsilon. It's bounded from above by 1 over epsilon squared times the variance of the thing. Well, that's this here, second moment of this here. And if you have the variance of this thing here, first of all, 1 over n, you can pull out of the variance with a square. And variance of the sum equals sum of the variances because they are independent. So this here is n times the variance of the first. But you divide by n squared, so 1n stays here. And by this n, which stays in the denominator, it converges to 0. Okay, that means we have, if they are in L2, we have convergence in probability. You might ask, well, if they are not in L2, but only in L1, but not in L2, that means they have an expectation. I mean, you could still formulate this here, because for the formulation, you only need the expectation. Only in the proof here we needed the variance, otherwise the proof doesn't work. So you can still formulate it and ask, does this hold? Does this hold if they only have first moments and not second moments? And convergence in probability here means they satisfy the weak law. So you can say it's a definition of something satisfies the weak law of large numbers if something converges in probability, if the mean converges to the expectation in probability. And the strong law of large numbers, the only thing which is different is you have almost true convergence and not convergence in probability. So that means the sequence satisfies the strong law. Today we have this. They're in L1 and they converge almost truly. I'm not going to prove this here in the video. I'm going to make two proofs, but in weaker cases. First case, x is in L4. As we will just see, that's easy. I mean, easy in the sense, it's 3 lines of calculation. I will also give a proof for x in an L2. which is still easy. It's not the proof that you already know, because the proof you already know only gives you here the convergence probability, but not the almost sure convergence. So we need something extra. And if you're then still interested in the proof where x only has an expectation, so x is in L1, you have to consult the manuscript. Okay, let's get started with the proof if x1 has a fourth moment. And we will always assume here in the proofs, without loss of generality, expectation of x1 equals 0. And we will always say that Sn equals the sum of the first n random variables. Yeah, one thing I need is that the expectation of Sn over n, okay, Sn sums n of these and expectations are linear, that's the expectation of x1. And what we are going to show is that here what we should show, we show that the sum over Sn divided by n to the power of 4 is finite, n from 1 to infinity, almost surely. Almost surely, that's what we are going to prove. And then we are done, because if this here is finite almost surely, Sn over n to the power of 4 converges to 0, and that means Sn over n converges to 0. And that's exactly what we want to prove, because Sn over n converges to 0, expectation is 0 without loss of generalities. So, well, we are done when we have shown this. And in order to show this, we show that the expectation of this thing here is finite, because a finite random variable is of course almost surely finite. In order not to get distracted by this n here in the denominator, I will compute the expectation of Sn to the power of 4. Sn is a sum. So what this here is sum times sum times sum times sum. And everything is independent. So, yeah, well, let me do this here. The sum to the power of 4, I could also write as a big sum, ijkl, xi, xj, xk, xl. That's the same. We're just multiplying out the 4 brackets. So when we have the expectation of this thing here, and the sum of all these expectations here, they are independent, which means, and they have expectation 0, which means, well, if I have, for example, I equals j equals k equals l, I have xi to the power of 4, that's not 0. But for example, if I have xi, but j equals k equals l, then expectation of xi is 0, while the expectation of xj times xk times xl must not be 0. It doesn't have to be 0, sorry. But the product is 0 then. And I have to ask myself what stays. So we just said k from 1 to n, expectation of xk to the power of 4. And that already means we need this L4 bit here. Yes, so that already makes sense. But more is true. What else stays here? So if I have the same index twice somewhere, I can have that 2 out of 4 times, and then KL from 1 to n, but k does not equal l. I have expectation of xk square xl square. And all the rest vanishes, because if there is one index which only stays once, the expectation of the product is the product of the expectations will be 0 anyway. And I can bound this here because of Cauchy-Schwarz. I know that this here is smaller or equal than the expectation of x k to the power of 4. Yeah. So Cauchy-Schwarz gives you that, this expectation of the product is less or equal the square root of expectation of a variance of xk squared times of xl squared to the square, so to the power of 4 actually again. And that means I can bound it from above by n times expectation x1 to the power of 4 plus 6 times. Well, having bounded this, I have to still count the number of things I have here. The point is at least that this here, the number of summonds here grows in like n square. So something like this here. And this means if I have the expectation of the sum n from 1 to infinity as n divided by n to the power of 4, this is now the sum over all n, or bounded from above by, well, some constant. In this constant here, I have the expectation of x1 to the power of 4, and I have something, 6 or something from here. But what stays is 1 over n square, and this is finite. So this is a random variable which is finite, so it's almost truly finite, and we are done. Okay. So we now already proved the law of large numbers, strong law of large numbers, for variables with 4 moments. But I still want to also do it with 2 moments. And I need one lemma from probability theory. That's this Kronecker lemma here. What I have x real numbers, y is a monotone sequence going to infinity. And I know that xn divided by yn is summable. So the yns go to infinity quick enough. And then I have that this sequence here converges to 0. So for this to hold, the yns have to be large enough. And that means not only this here is finite, but the sum of the first n of the case divided by yn goes to 0. Okay, let's prove this. Let's use z0 equals 0 and define recursively zn is the sum over xk over yk, k from 1 to n. Then I know from this here that it has a limit. So this here converges to z infinity by assumption as n goes to infinity. And I can also write that, just write xk equals yk times zk minus 1. zk minus 1 by definition is xn divided by yn. Zk minus 1 is where am I here? Xk divided by yk, times yk equals xk. So that's it. Let me also define y0 is 0, which we will need. And then what should converge to 0? Well, it should converge to 0, 1 over yn times sum over the xk's, k's from 1 to n. And let me rephrase the xk's like here. 1 over yn, sum over yk, zk minus zk minus 1. K from 1 to n, and the only trick you can do with such a sum is shift the index, but not for both terms, because it's a sum in the sum, or a difference in the sum, only for one of the two, and then see what happens. So, okay. I could also sum up down from 0, because y0 is defined to be 0. That's not a problem. Let me, for the first thing here, for this is xk times zk, let me pull out of the sum the nth term, which is then here yn zn, divided by yn equals zn. Plus 1 over yn. Sum k from 0 to n minus 1 xk zk minus sum k from 1 to n yk minus zk minus 1. Okay, zn. Then let me switch signs around. Minus 1 over yn. And here I have one sum k from 0 to n minus 1 and one from n1 to n. And I will shift indices here. In the sense I have sum k from 1 to n. And then I write xk minus 1, zk minus 1. Let me also, and that was not a minus, that was a times, right? Yk times zk minus 1. And I have to deal with this first. Yk zk minus 1 times yk. And when I shift indices, I have to write here yk minus 1 times zk minus 1. So yk minus yk minus 1. Like this here. Okay, then the z's here by assumption, they converge to z infinity. So if n is large enough, the sum is over all these z's here, which are basically constant. And that means this here converges as n goes to infinity to z infinity minus, and here I can pull out the z infinity as well. And what remains, 1 over yn, sum k from 1 to n, yk minus 1. And of course, this here is a telescope sum. Converts to, that is yn divided by yn is 1, and that means here this is exactly 0. Yeah. And now we have proved the Kronecker lemma. Let us now come to the strong law of large numbers in the case of second moments. Proof for x in L2. And we want to use the Kronecker lemma. And the Kronecker lemma, first of all, has this here, xn divided by yn sums. So what is yn? Yn is identity, so I consider the sequence x1 divided by 1, x2 divided by 2, and so on. let us briefly compute the sum of the variances of xn divided by n from 1 to infinity. Well, that's easy because variance of x1 equals variance of xn equals variance of x1, and that's variance of x1 times sum over 1 over n squared, which is finite. And then we had last time, I have here random variables, and this variance of the sums converges, like here. Then this here converges almost sure, so the sums converge almost surely. So we have here that sum xn divided by n is finite, almost surely, n from 1 to infinity. And now we have the Kronecker lemma. Xn by n is finite, and then we have that the sum over the xk's divided by n goes to 0. So 1 over n, sum over the xk's, k from 1 to n, goes to 0 by the Kronecker lemma. And we're done with the proof where x is in L2. Just as an application, let us study convergence of the so-called empirical distributions. What's the empirical distribution? We have randomals, real valued, or maybe they don't really have to be real valued, but nevertheless. When I have these, I can make a probability distribution out of them. And in statistics, that's what you always draw when you have some data or so. You want to see how are they distributed, how is my data distributed. You draw something like the empirical distribution. That's the delta mass at xk and, well, sum over all n. That's the empirical distribution. And if they're real valued, you can not only have the probability distribution, which is the empirical distribution, but also the empirical distribution function. So at every point x or so, you ask yourself, here's 1, what's the fraction of randomers which are below this x here? And then you get also some distribution function. But since you only have finitely many n here, this thing is not absolutely continuous, but a little back measure, but it's a counting measure, as you see. And there's the so-called Glivenko-Cartelli theorem, which tells you that the distribution functions converge in the soup norm actually to the original distribution function from the distribution where they came from. And let me here not show the uniform convergence, but the pointwise convergence. Pointwise convergence. So let x be some value in R. And fn hat at x, that's the distribution function, indicator xk is more equal than x, k from 1 to n. So this here is the number of x's which are at most small x. Okay, these are independent if the x's were independent. And what's the expectation of one of these? So expectation of 1xk is more or equal to x. That's the probability that xk is more or equal than x, which is the distribution function at x. So what is written here in the result is an expectation. It's an expectation of this here, which arises also in the first term here. Yeah, and then that's only an application of the strong law of large numbers. I mean here for pointwise convergence, because the expectation of the mean value of these here converge to the expectation, which is exactly this here. And then for the uniform convergence, which I'm not going to show you here, you need that the distribution functions are only between 0 and 1 and also increasing, so not very much can happen in order to destroy the uniform convergence. And well, that's it basically. So we have now completed, I think, all results where we wanted to deal with almost sure and convergence probability. And next time we're going to start with a weaker form of convergence, which is called weak convergence. See you then.